now keep the concept of cardinality in mind. We can talk about partial orders. So here's the definition of partial orders from Wiki, and has a diagram to illustrate it. We just talk about cardinality. The minimum cardinality is 0. That is cardinality of an empty set, a D-empty set. And then 1 is the cardinality of every singleton. And 2 equals to any binary sets. 3. And if we have a cardinality n, that means all the sets x, y, z have the same cardinality n. And they are isomorphic because we can establish bijection among them, between any pair of them. And we have cardinality of countable infinite numbers, like the set of integer numbers. And bigger set like real number. We can observe that there's a relation between those cardinalities, their numbers. At the beginning, they are numbers, natural numbers, then infinite, different kind of infinity. So they're not simple numbers, but they still can compare. So this symbol, less symbol, essentially is a kind of arrow. It's an arrow. Like we can establish an arrow between 0 and 1. That means 0 is less than 1. Or we can have 1, 3. 1, 3. 1 less than 3. So we can rewrite this line into 0, 1, 2, 3, 4, n. Now let's check the definition of partial orders. So a reflective weak non-strict partial order, we can ignore that. We always talk about non-strict partial order. Commonly referred to simply as a partial order is a relation. It's a relation, it's a binary relation between a pair of elements on a set. The set P here, this is the set. This is a set of 0, 1, 2, 3, n. This is the set. We can denote it n. We denote it n. It's like nature number, but obviously it has kinds of infinite numbers. So we use n. And the binary relation between them has 3 axioms. The first one is reflexivity. Every element is related to itself. That means 0 less than 0. It's not looks so good. So we can use less equal symbol instead of less symbol. So we can write them like this. Then everyone is related to itself. So we satisfy the reflexivity. Next, anti-symmetry. If A less equal than B and B less equal than A, then A equals B. That is, no two distinct elements precede each other. So if we have X, Y, and Y, X, then we have X equals Y. So what can we think? Recall that if we have two sets, X, Y, they are sets. And if we have X less equal than Y, that means X, there's an injection from X to Y. And if X greater or equal than Y, that means there is a surjection from X to Y. Both these two conditions are satisfied. That means we have a bijection. Bijection gives X isomorphic to Y, and XY have the same cardinality. You see that? You see that? This condition combined together makes cardinality equal. That is the idea of antisymmetry here. And the third one is transitivity. Transitivity of X, Y, Y, Z. That's simple, right? Here we have 1 less equal than 3 because we have 2 as an intermediate item. So if 1 less equal than 2 and 2 less equal than 3, we have 1 less equal than 3. So 1 less equal than 2, 2 less equal than 3. So we have 1 less equal than 3. So we can transit the arrows. So for simplicity, usually we do not write those composite arrows. We just write the adjacent arrows. Otherwise, the diagram will be very complicated. And it's interesting that we have a takeaway that every partial ordered set this is a set. The set equipped with a partial order became a partial order set is a category. We have studied several categories. The first one is the video signal port types. The other one is linear space. And the category of sets and the category of finite sets. We have 4 examples of category. They are looks like a very trivial, right? But here, it's an interesting result that every partially ordered set is a category. Why? Let's review the definition of category. A category have a collection of objects and morphisms and composition, identity, associativity. Let's check here. If we have a partial order here, partial order set every element of the set is an object. Element as object. Second, the partial order as arrow. So we replace those less equal symbol as partial order, replace them with arrows. That gives us an intuition that they are essentially arrows. They are essentially arrows or morphisms in the category. And three, identity. Every element as an object has an identity. Why? Because the law of reflexivity, right? Here, A less equal than A means there is an identity arrow from A to A. That from A to A, the source, the destination. Good. Fourth, composition. We have talked about composition before, just now, the transitivity. The transitivity is just composition. If we write them like this, A less equal than B and B less equal than C, that is essentially A with an arrow and B, C. So the composition is nothing but the composite arrow. Composite and ignore the intermediate B, right? So we have composition. And five, associativity. It's easy for us to validate that the composition of arrow satisfies the associativity. Okay, so we got this takeaway that every partially ordered set is a category. And then we back to the set. Here is a set. I copied this example from Wiki. The set, let it be X, Y, Z. It's actually a set. So it's an object of the category of sets. And we have the Px as the power set of X. Or we can write Px equals to any subset of X. So subset of X. So we have 8 subset. The empty X, Y, Z singleton, empty, and the binary and X itself. So it's interesting that here is a partial order relation. You see, ordered by inclusion. And it became a partial order set. So what's the meaning of partial order? What's the meaning of partial? Partial means that not every element can be compared. We can compare the order of X to xy to xz. Let's say there is an injection from x to xy. We can inject x into x here. And we also have injection xz. So the injection is essentially inclusion. But we cannot inject x into yz, right? So we cannot compare them. So the injection can only establish between x to xy and x to xz. So not every pair of the subsets can have the relationship of injection. So it's partial order. But x can be injected into x itself. So this is the reflexivity. And we can composite, like an empty set can be injected into x, and x can be injected into xz, and xz can be injected into xyz. So the empty set can be compositely injected into xyz. Okay, so this is a partial order set. And as we have discussed before, if we have two sets, x, y, and the cardinality of x is less equal than y, we can establish an injection from x to y, or denoted by x arrow y. Right? So let's review this. We have a partial order set, meanwhile a category of the set of cardinality. This is the set of cardinality, equipped with a partial order, so it became a partial order set. And we have different kind of set in the category of set, like empty set, singleton, binary set, 3-point set, n-point set, and natural number, integer number, set of integers, etc. The collection of all the sets is the category of sets. The category of sets. And every set has a map from the set into its cardinality. And here is a category, and any partial order set is also a category. So there's a map from a category to the other. That kind of map is called functor. Distinguished from a function. Function is map from set to set. Functor is a map from category to category. And formally, we write a functor like this. Category set maps to the category of all the cardinalities. An object of set, that means a set, maps into the cardinality of X, and another object maps to Y. And there's a relationship between X and Y, right? The relationship is, in set theory, the relationship is X injected to Y. That's the arrow. So the injection arrow as a whole is mapped into an arrow of less equal than. So here we see that this functor, we call it the functor of cardinality. It preserves the structure of partial order set. The set equipped with injection is a partial order set. The cardinality equipped with less equal than is also a partial order set. So the functor of cardinality preserves this mathematical structure.